Integrals can be really challenging to compute, especially when we're talking about double or triple integrals. So what are we going to do? Are we going to learn like all kinds of cool new techniques like parts and partial fractions and all these sorts of things? No, we're not going to do that. We're going to focus on one really fundamental, useful technique. This involves changing coordinates. This is really helpful for certain difficult integrals. We're going to start off slowly with an example that should be somewhat familiar. We're going to focus on polar coordinates, something that we have seen maybe back in our treatment of single variable calculus. Remember, x equals r cosine theta, and then y equals r sine theta, where r is the radius, square root of x squared plus y squared, and theta is the angular variable given by arctan of y over x. Now, you've probably used polar coordinates in the past to work with certain types of curves in the plane, things like that. What we're going to focus on now is how to transform to polar coordinates to make double integrals simpler. And the way that we're going to approach this is by thinking in terms of the area element in polar coordinates. Now, you have to be a little bit careful because this area element is not dr d theta. Instead, it depends on the radial coordinate. So if we do a little bit of thinking, a little bit of geometry, then we arrive at an area element of r dr d theta. This kind of makes sense. It's got the right units. R and dr both have units of length. One way that we would argue this at the infinitesimal or elemental level is to say that we zoom in and we look at a small area element. And in the radial direction, it has length dr. And in the angular direction, it has a length of r times d theta. As you change r, that length is changing. And it's changing linearly in the radius. Okay, so let's assume that area element and turn to a simple, but maybe not so simple, integral. Let's say I want to compute the double integral, sine of quantity, x squared plus y squared, as x goes from 0 to root pi minus y squared, and y goes from minus root pi to plus root pi. The first thing to do is to consider the domain of integration. Look at those limits of integration and see what shape does this correspond to. Well, if x goes from 0 to root pi minus y squared, then it's sweeping from left to right. And that upper limit, root pi minus y squared, that comes from the equation x squared plus y squared equals pi. That's defining a circle in the xy plane based at the origin of radius square root of pi. And now the limits on y make perfect sense. As you're going from minus root pi to plus root pi, this is really giving you a semicircle in the plane, and that is very well adapted to polar coordinates. Likewise, when we inspect the integrand and we see that x squared plus y squared staring right at us, that's like a big flashing red light to use polar coordinates because that x squared plus y squared transforms to r squared. So you're really integrating sine of r squared. The limits of integration become really simple. The radial coordinate, r, goes from 0 to root pi. The angular coordinate, theta, goes from minus pi over 2 to pi over 2. And the area element, dx dy, transforms to r dr d theta. So with that nice-looking integrand, with those nice numerical limits, now we can solve this integral. If I integrate with respect to theta first, using Fubini, this is really simple. D theta integrates to theta. Evaluate from minus pi over 2 to plus pi over 2. Now, for the second part, the integral of r times sine of r squared dr, well, I can either anti-differentiate that in my head, getting minus cosine of r squared over 2, or I could do a more formal u substitution, letting u be equal to r squared and following the usual process. When I evaluate these integrals at the limits of integration, I get pi over 2 times quantity minus cosine of pi plus cosine of 0, giving me a final answer of pi. Does this make sense? Yes, it does make sense. On this domain of integration, sine of r squared is always going to be positive, and my final answer is positive. Yeah, this kind of makes sense. Feels pretty good. I don't think we made any mistakes. Now, what I want to point out is just how useful polar coordinates were in this context. This would have been a very challenging integral in Cartesian coordinates.